Okay, let's see. Good. So, as I mentioned, I will explain the problem 3.2 or problem 3 more in detail because, yeah. As far as I see, only 2 or 3 students answer the question is problem 3.2 completely. So I don't know. So if you again encounter the problem network, just let me know. I'm not. I think I can do little on the network problem, but just let me know. And if you have a question, just send me a message via WeChat, as we have done in previous lectures. So, so the in QED generating function J eta bar can be written in terms of exponential. Sorry, and one student told me there's no I here. And delta eta alpha. Gamma u alpha beta delta eta bar and the beta delta j mu and acts on z0. So z0 is just a free one. Is the free is the dA deep psi d psi bar exponential I d for x free and a bunch of L gauge fixing plus J mu and mu plus eta bar psi plus psi bar eta. Free is this one is just f mu nu appropriate factor plus psi bar I partial slash m psi. Okay, so this is the so then this will create the interaction term. So this essentially will create the interaction part, which is something like a minus e psi bar s slash psi. This is the essentially what's the effect of this derivative. And then after performing Gaussian integral, this can be understood as the some number times e to the I'm going to be schematic jdj, and then minus eta bar s eta. And of course, there's an integral involved. I'm going to skip. So in detail, you can just look at the solution set. So this one's set, and then so you just apply so this derivative by perturbatively. So therefore, so this is the what's going to happen. So and then here, so if you do the Taylor expansion for exponential, so what you will get is 1 minus e to the sum. So this derivative d for x delta eta gamma delta eta bar delta j. So this is the first order, and the second order of e is this one, the same thing. Square and blah, blah, and which axon is easier. So therefore here, if you look at this one, so z1 tilde is given by 1 over z0, and then so I'm going to write this one is 1 over z0, and then 1 plus minus e z1 tilde plus minus 1 e squared z2 tilde, and so on. I mean, strictly speaking, you have to include higher order correction. So here you have some, so this derivative acts on z0. Okay. So let me write down derivative d for x d eta gamma delta j that acts on z0. Okay, so then so you just apply this eta bar j derivative on this exponent. And for instance, the one way to act is just act eta bar derivative on here, okay? On here, then you get the s. So what you will get is 1 over, of course, z0. Then what you, so if you act eta and eta bar derivative on here, what you will get is a trace of gamma and the s x minus x. Okay. So since, as you can easily see from here, alpha and beta, then take derivative of here, and gamma is here, right? Gamma is here. So therefore, you need to take a contraction between alpha beta and s alpha beta here. So which will give you a trace. And the position of all the position is x. So therefore, it becomes x minus x. Okay. And J acts on here. That will give you, of course, there's the 1/2 here. I'm going to be very schematic, so I don't care about minus or plus quotient and so on at this moment. If you want, you can just check by yourself by explicit calculation. So you just J acts on here, you get the dj, same dj of x. Everything depends on x, and then ddx, d4x. That's first term. Another way to apply is you just do the Taylor expansion of it exponential. That will give you the for instance, if you do the exponential e to the eta bar s eta, so that will give you eta bar s eta and 1/2 eta bar s eta and eta bar s eta. Okay. So and so on. So instead of acting the eta and the bar on leading order, you can just apply eta on one group here, and eta bar acts on the other group here. Okay. So that will give you two propagator, and the eta bar and the eta left. Okay. So and the J acts on the as before, but this will give you d4x, and abruptly I'm going to omit all the integral, but what you will get is essentially, so if eta acts on here, what's left is eta bar s. Okay, and if eta bar acts on here, what you get, what's left is s eta. Okay, s eta. And then J acts on here will give you dj. Okay. You have to restore all the variable appropriately. So this is the first Z1 Taylor, and as you can easily see, so the trace of the fermion propagator will give you just this one, the loop, and dj will give you the yeah, I think this has to be, I mean, strictly speaking, dx minus x1 jx1. Okay. So this point is x and x1, okay. And you have to restore d4x1 appropriately. So I'm going to be really schematic at this moment. So therefore, this will give you a Tadpole diagram. So the trace of sx minus sf x minus x is just to give you loop, okay? And from here, from x, you get the photon propagator. And here, you have a different variable x1, x2, x3, and then which is connected to the point x. Okay? So you get just an electron vortex. So this is, as you can easily imagine, so z is the generating function of all the connected, sorry, not connected, all generating function, all the correlation function. And then this is leading order. So the Z1 Taylor is the leading order. So you just come up with all the diagram which has one vertex. And these two are the exhaust all the possibility with leading order. Okay, so that's what you do. And then the question is this one, which is tedious. So I'm going to erase. And as I explained to you, so this diagram vanishes because Tadpole diagram and by symmetry. So Z2 Taylor is essentially so probably a factor to Z0. Then so two derivative acts on Z0, that will give you 1, 2, 3, 0, the derivative Z0, one axon will give you Z1 tilde, right? And then you have to restore all the derivatives, gamma, eta bar, delta j, and then integral. I'm going to very schematic. And you just apply these derivatives on Z0, Z1 tilde in all possible ways. So for instance, this will give you, I'm going to be schematic, d for x. For instance, eta can act on Z0, and eta bar j can act on Z1 tilde. So therefore, one possibility is something like a Z eta, Z0, and gamma, delta square, delta eta bar, delta j, Z1 tilde. Okay? And so on. So eta bar j can act on, you have to exhaust all the possibilities how these three derivatives act on Z0 and Z1 by using Leibniz rule. And also you have to be careful about the swapping eta and eta bar because they're Grassmannian derivatives. Okay, so that's you need to do. And for instance, let's look at this factor. So Z0 is essentially e to the j dj minus eta bar s eta. And eta acts on here will bring you eta bar s. And if you look at this one, so Z1 tilde is given here, and then so eta bar and j derivative can act on only this part. Okay, so therefore that will give you get rid of eta here and j here, get rid of eta bar and j here. So which means that essentially what you will get is you just connect. It depends on how you draw the diagram. But so for instance, this is eta bar and the j is connected. Okay, and that is connection is connected, and furthermore is connected to here. Okay, so therefore. Essentially, this will give you the propagator, and then so this will give you. So you need to. So j and the eta bar are connected, which will give you this diagram. Okay, and this point should be connected to eta bar s. Okay, eta bar s is this one. That will give you this diagram. That will give you this diagram, and you have to exhaust all the possibilities, and which is written in the solution one. So you can check how to do that. But you understand. I hope you understand how essential idea how to act the eta bar j derivative and then find the corresponding diagram. Do you understand? I think I spent 15 minutes, so I'm going to stop. If you have a question, just ask me later. Okay. And you have to be careful about all the signs and so on. Okay. How is the network today? Is it so far okay? Just reply to me via WeChat. Okay. So, um, so last time, so we just introduced so Wilsonian effective action and also Coulomb-semantic equation. Which takes the following form. So mu plus beta lambda pressure lambda plus beta n square pressure n square plus n gamma phi gn x lambda n equals 0. And this is called anomalous dimension. Some book treat like this part is some big book. Some people write like this way. Some people write like this way. I mean, it just depends on notation. And this gamma is called anomalous mass dimension, and so on. But it depends on a book. It really depends on book. Some book treat use this notation. It depends just notation. For instance, yeah. So that's what we have introduced. And for instance, so computation of beta function. So at the end of the lecture, I introduced the beta function in massless theory, QFT, any dimension. So that the so what I have done is the so what I have done is just write down the wave counterterm for wave function renormalization in gamma square mu square plus finite term. So then anomalous dimension can be written in terms of 1/2 mu pressure mu delta z is minus a. Okay, so the network is good today. I mean, I think it really depends on network of university and also the situation of Bilibili or Bijan. So I cannot control it somehow. So and also this is I think zi and ai phi i. Okay. Yeah, I think online Bijan is better than Zoom. And also delta lambda coupling constant is minus b log lambda square, and it means square plus finite. If you write like this way, and what we have computed is beta of lambda can be written mu pressure mu and minus delta lambda plus 1/2 lambda sum of delta zi. Okay. So which can be written in terms of minus 2b minus lambda sum of ai. So this is the massless. That is important. A massless QFT. So that's how we compute beta function for massless QFTs. So that, as an application, I'm going to find a beta function for the QED, quantum electrodynamics, massless. So massless QED. So now I assume the electron mass is 0. And then so if you use the dimensional realization, so this you can just compute by using dimensional realization. This can be computed for pi square gamma 2 minus d over 2 get over mu square 2 minus d over 2 plus finite. And also delta 3 is given by minus e square 4 pi square 4 over 3 gamma 2 minus d over 2 mu square 2 minus d over 2, okay? Plus finite. So these can be computed by using the result of Pascal-Schroeder 10.4. I already forgot. 10.3 or 4. I already forgot. Just set m squared equal to 0 and perform the integral over the final parameter. You get this one. Of course, you have to restore the mu squared appropriately. So, I mean, this can be just computed by brute force way. Okay, so then now I'm interested in here. So we want to apply this formula to master's QED. To this end, I just look at again 3-point function where the counter term is given by of course the counter term is given by IE delta 1 and gamma 1. Okay. So that of course delta 2 and delta 3 are wave function renormalization for of course a Feynman and a gauge field, and delta 1 is the counter term for the electron vertex. So this delta 1 corresponds to delta lambda, and delta vi are the delta 2 and delta 3 in this case. And so we just brute force way apply this one on here. So therefore beta of E is mu partial mu and minus E delta 1, which is just corresponds to this one. Delta lambda is E times delta 1, and then you have a 2 electron vertex, which is 1/2 E. So now lambda corresponds to E. And you have a two leg for Feynman, so therefore 2 times delta. Okay. And also there's a 1 photons, which will give you 1/2 E, or maybe delta 3. Okay. So that's, and you plug this result into here, and then what you will get is E cubed 12 pi squared. Just plug this result into here, and then of course d is equal to 4 minus epsilon. Okay. 4 minus epsilon. And plug that into here, you get this result. And one can also apply gamma this anomalous dimension, and then anomalous dimension for the gamma 2 is just apply the same formula over there, and then what you will get is E square 16 pi square, and gamma 3 is you just apply the same thing. So of course the relative ratio 4 over 3. So you can easily see that this has to be E square 12 pi square. So these are anomalous dimension of QED. Okay, so once you prepare for master's QED, once you compute counter terms for wave function renormalization and the coupling constant, it's easy to compute anomalous dimension and better. And essentially, you have done even with math. In homework 2 and problem 2, even with math, you can compute gamma and better if you have done the homework. Okay, so that's the QED case. And furthermore, so as I mentioned last time, so this E of mu is indeed gives the so E of mu or lambda of mu in general, lambda of mu is the coupling constant that measure coupling constant measured at scale mu. In particular, in QED case, it's easier to introduce the so-called fine structure constant E squared over 4 pi, fine structure constant, and apply this beta function. So the definition of beta function is, of course, beta of E is just a dE, d log mu. And just using redefinition of the redefinition and integrate out the beta function, what you will get is alpha of mu, dependence of mu, is given by alpha star divided by 1 minus 2 over 3 pi alpha star log mu where the alpha star is alpha mu is equal to mu star. Okay, so you just set the initial value for fine structure constant at the mu star. Then of course mu star over mu star vanishes, so therefore you get alpha star. But the dependence of mu is just can be incorporated in this formula. And of course, if you apply d log mu onto here, you get the corresponding beta functions. That you can easily see that. So this is the dependence of fine structure function on dependence of on the scale you mentioned. Okay. Yeah, I mean, you can easily see, right? So d alpha d log mu is, of course, is given by, so if you apply this formula, it's easy to find 2 over 3 pi, and then alpha square. Okay. Then you just restore, plug back into here, what you get is the 2e 4 pi dE d log here, and you just apply the same thing to 3 pi e squared 4 pi square, and this is of course beta function, and if you cancel that one, you get this one. That you can easily check. Okay. So that's the dependence of fine structure constant on the scale mu at one loop level. Okay. So that's of course we just only here only compute the one loop order, and that has been done by essentially showing confinement on Naga. In the higher loop order, lots of effort has been made by many people, including Kinoshita at the Yale University. And now I explained to you in the first lecture of the QFT1. I think it's now 4 or 5 loop order, and it's the most precise matching between experiment and theory. Okay, so that's the beta function of QED. So let me let's talk about how the data function will tell you how the running coupling constant behave. So this is the running coupling constant. So just okay, so let's maybe first let's talk about the RG flow of dimensional flow operator. So let's suppose Lagrangian has, so in d dimension, Lagrangian has something termed like a dx ci operator di. So then, so this is a local operator of mass dimension. Therefore, the mass dimension of C I is d minus di. Okay. So that's the so the current symmetric equation of endpoint function can be written as follows: 0 is equal to mu pressure mu plus beta pressure number plus n gamma phi plus gamma I ci pressure. Okay. Acts on Gn and algebra. Okay. So endpoint function. Okay. Here now gamma I. So it depends on. I mean, that's what I meant the last time in the beginning. Gamma m and so that can be just rewritten in the, and this is dimensionless. Can you see this part? Okay, hopefully you can see that. Dimensionless parameter. So that's how I write here. It just depends on notation. Okay, so that's the and suppose so we just write down the Ci as follows. Since the scale we introduce has a mass dimension, so usually it has the behavior something like a d minus di, where the gi is the so Ci has mass dimension d minus di, and so if you assume the series is massless, the only parameter that has mass is mu. Okay. So therefore, so the Ci has to be proportional to mu to the d minus di because of the dimensional reason, and Ti is massless parameter. Okay. So not massless, dimensionless. Okay, sorry, dimensionless. Sorry, dimensionless. Dimensionless parameter now. So then, so one can write down this Coleman-Weinberg equation by using Gi instead of Ci. Of course, as you can easily see, if so, Gn also depends on. Okay, maybe you cannot see that. So this acts on Gn, something like x and also lambda and Ci, and also this depends on mu. That acts on here. Okay, this is Ci. Ci can act on mu. So if you write down Ci is equal to Gi times mu to the d minus di, if the mu derivative acts on Ci, that will give you d minus di. Okay, that has to be cancelled with C derivative, so that the this equation becomes as follows: mu pressure mu I plus. I'm not sure if you can write down everything. Okay, let me try. Beta pressure lambda plus n gamma phi. But now, so the effect of d minus di acting on mu has to cancel here. That would be the just opposite d plus di. Okay. Pressure G. Gi. Pressure Gi. Acts on Gn. So and then so you can just write down this one is beta Gi. Okay. So then, so by definition, so the d Gi d log mu is beta Gi, which is equal to gamma I plus di minus d Gi. And suppose we assume that the lambda, so that you can apply the perturbation theory. Lambda is much smaller than 1, and also Gi is much smaller than 1. So this is if the perturbation theory is valid, then so Gi, so you can just assume Gi is Gi mu star, and e to the di minus d log mu star. So if you solve this the equation, so if you assume this one, so this means that the gamma I is really small. So if you assume this one gamma I is very very small, let's see, yeah. So here I just assume the let's see, it's an anomalous dimension, or this gamma mu is very small because of this assumption. Just a moment. Okay, maybe this is also another assumption I made. Sorry. Okay, suppose all the Gi is very small, and then and also gamma I is very small. Gamma is very small, so then you can just ignore this part, and if you ignore this part, the solution of this this differential equation is given by this. So which is gi of mu star and mu star to the di minus 3. So therefore, so this is already we have seen from Wilsonian effective analysis of the Wilson effective action that if the mass dimensions of Ci is positive, then the Ci is of course super normalizable. Super normalizable, so that the gi mu is much greater than gi mu star, okay, for IR, which means the mu is less than mu star, as you can easily see from dimensional analysis. Okay. So therefore, even if the Lagrangians at the UV Lagrangian has very small gi or a small value of Ci, so if you go to IR, so the gi becomes relevant, okay, relevant in an IR. On the other hand, if the mass dimension of Ci is less than 0, okay, so then Ci is normally normalizable. Ci, so that the gi mu is much less than gi mu star at IR for perturbation theory. That's what perturbation theory tells us. Okay. So perturbation theory tells us that if the coupling constant mass dimension of coupling constant is less than 0, then so the term becomes irrelevant. It's negligible. Whereas if the mass dimension is positive, automatically so the Lagrangian should include this. So the coupling constant this parameter becomes relevant at the IR. Okay. Okay. So that's the case. So therefore, so people call this one is relevant operator. So relevant operator. So the OI, so ODI is called relevant, and ODI in this case called irrelevant. So, and the question is, what if the Ci is equal to 0? So this is, in that case, OI, ODI, or essentially this OD, is called marginal coupling. Marginal operator. But however, as you know, as already encounters the FIFO theory, so for instance, FIFO term is marginal operator. But as we have seen in the perturbative analysis, at one loop, the coupling constant depends on mu. Okay, so therefore, for instance, I can just write down here. So the example is just this term, 5 for in t equal to 4. Okay. But we already know the beta of lambda is smaller than 0. Okay. So therefore, it depends on the scale. So it depends on scale, and then we will see what's going to happen in the IR and the UV for FIFO theory. But in that case, so therefore, the marginal operator is often depends on the I'm sorry, beta, lambda, beta or lambda. Often depends on scale, but if beta of lambda is equal to 0, if, okay, okay, so maybe I'm going to let me erase here. If beta gi equal to 0 for operator D, then operator D is called, this is called exactly marginal operator. So this is called exactly marginal operator. That will give you so-called the space of the so-called conformal field theory. This is a very, very important topic. And then if you use supersymmetry, this often has some geometric meaning. For instance, it's a bit advanced topic, but if you use supersymmetry, for instance, for the n equal to 2 supersymmetry, so this exact marginal operator just can be identified. This is a research topic of the modular space of Riemann surface, and so on. So it's a very rich mathematical structure one can find once you include supersymmetry. But anyway, so that's the what the operator is called depending on the dimension and the beta function. Okay. So this is dimensional. So this is consistent of the power counting analysis and also the Wilson effective action and so on. And for instance, if you go to the fivefold theory, but if you change the dimension, so let's assume everything is here. Okay, assumption. So if you change the dimension, so if you consider the fivefold theory in dimension d, so then beta function of lambda. So of course, so I assume the 4 factorial in Lagrange, but not 4 dimension, in d dimension. Then so this analysis I already erased here will tell you that it's the leading order, so this should be depends on d minus 4 of lambda, and one loop order we already computed lambda square 16 pi square. Okay. So that's what we have computed. So this is this is 3. So this is one loop order. We computed, so this is coming from dimensional analysis we have done. Okay, So of course, when d equal to 4 cases, there's nothing here. But if you go to the arbitrary dimension d, lambda has the mass dimension. So therefore, the leading order has to be okay. And then, so let's look at the more detailed more in detail about the Riemann coupling constant dependent on beta function. So any questions so far? Let's see. Okay. So as you can easily see from here, of course, so if D is less than 4, then FIFO term, this FIFO term is super irrelevant. So essentially, so now I'm looking at the D dimensional form. So that's, you can easily see from the dimensional analysis. Okay. Okay, so sorry, I think I'm saying something stupid. Sorry, I think the coupling constant is the other one. Sorry. Okay, so sorry. So this one I have to be careful. Sorry. Let's see. I have to be careful about this one. Sorry. So FIFO theory is sorry. I'm sorry. I told you wrong. Sorry. So FIFO theory. So if lambda is big enough, Sorry, I told you wrong. If lambda is big enough, then gamma I cannot be neglected. So neglected in this equation, dgi d log mu is equal to beta I, is equal to gamma I plus di minus d of g. So therefore, so this can change if So the perturbation theory is not applied. So this so therefore the dimensional analysis is no longer true. So as I mentioned, the dimension I told you. And then the typical example, that one is five-fold theory. Sorry. So five-fold theory in arbitrary dimension D. Okay. Sorry, I think I told you completely wrong thing. And then so this behavior really comes from dimensional analysis, and I'm going to explain what's going to happen for this one. So sorry, I'm going to explain. I'm sorry, I told you wrong. So the running coupling constant depends on beta. So if beta of lambda so greater than zero is greater than zero, so then lambda of mu increases as mu increase. Okay. So so therefore we start with the so essentially what we would expect is lambda and mu, and depending on how the initial condition, so we assume like something like this one. So suppose there's a one here. At the small low energy scale, so you can apply the perturbation theory. Whereas the if the the value of lambda approaches to 1, no longer perturbation theory is valid. So that you have to also consider another effect, so-called non-perturbative effect, and so on. But if the non-perturbative analysis beyond the around point would still tell you the beta is 0, then the theory will hit to so-called lambda pole. Okay. Lambda pole. I mean, lambda pole means that if mu goes to infinity, lambda goes to infinity. Okay. If the even non-perturbative analysis would tell it all the way to the mu goes to infinity if the beta function is positive. Okay. Then it goes to lambda pole. And such a theory should be replaced. So if this is the case, the theory has to be replaced by the theory has to be replaced by the different the so-called the well-defined QFT, which is called sometimes called UB complete theory. Okay. As an example, so for instance, so this includes example in the QED, and also five-fold theory in dimension 4. So we already see that the beta function in D4 of lambda is, as I write down, well, there are 3 lambda square, 16 pi square. Okay. So it's positive value, and so some non-perturbative analysis, so-called lattice calculation, and so on, will tell that even go to the strong coupling regime, beta function is always positive. So therefore, it has to be replaced by something, some well-defined QFT. Because I mean, if you go to UV or really high energy, the Kaplan constant goes to infinity. So series is not well-defined. So in the QED case, we know that this one is replaced by so-called electroweak theory. Weak theory is U2 times U1 hypercharge. That's what I'm going to explain in the later part of my lectures. So this is the one possibility. And then, sorry, I want to keep this one. And if beta function is negative, okay, so negative, okay, maybe, okay, let's assume this one. Let's still keep thinking about the positive case. So what if the IR? Okay, suppose beta of lambda goes to 0 when lambda goes to 0. So for instance, if we go to the opposite region, IR, the series well-defined IR, and also if this is the case, if the IR is start with something like this one, okay? It starts with 0. Then this point is called the Gaussian fixed point. It's called Gaussian fixed point. So this point is called Gaussian. Where the so essentially this is free theory. Essentially free theory. So the coupling constant goes to 0. Okay, free theory. So for scalar theory, it seems something like a partial phi square minus m square phi square. So this is the Gaussian theory for scalar theory. So this is the called Gaussian theory. And suppose there is some effect. So that there is some effect at the non-perturbability, something like a. So you start with Gaussian theory where lambda and the beta of lambda. So if you turn on some the coupling constant lambda, then beta function is positive, and as you know, so that if beta function is positive, if you go to UV theory, so then lambda increases. But from some non-perturbable effect would tell you that it decreases. Sometimes, so this non-perturbable effect we just how to say bend the curve of beta function to the 0, okay, at the UV. Then so this point is called so the beta function vanished, and its non-perturbable effect will sometimes give you the beta function vanish at some point lambda star. So beta lambda star is equal to 0. So this one is called so this one is called when mu goes to infinity. So when mu goes to infinity, then lambda goes approach to lambda star. Okay. So then once you reach this point, so the beta function no longer coupling constant lambda do not run because beta function is 0. Okay. So now so this is lambda star is called UV fixed point. Fixed point means the coupling constant lambda is fixed. It do not run depending as you change mu. So that's the UV fixed point. And suppose you have the opposite case. Okay, so this is the suppose the beta function is negative. So then lambda decreases. So as mu increase. So therefore, the theory is the opposite. So then the lambda and the mu. So as you go to the UV or higher energy, so the lambda decreases, something like this one. So therefore, it's called, so lambda goes to 0, when mu goes to 0. Okay. Mu go to infinity, mu go to infinity. So this is called asymptotic freedom. So this is called asymptotic freedom, asymptotic freedom. So when lambda goes to 0 becomes the free theory. So when asymptotically, if you go to, as you go to increase the energy, so the theory become free. That's called asymptotic freedom. And then as we will learn, so we will learn that the QCD, not QED, QCD, quantum chromodynamics, is one example. And then, so the question is, given that asymptotic free theory, the question is what's going to happen at IR. That's very, very important question. So that's usually essentially the physicist who is working on the QFT should answer. And then, of course, that's one of the cases for QCD. So QCD is asymptotic free theory, and the question is what's going to happen IR. And that's very, very difficult question. And there's lots of interest phenomena occur, so-called mass gap, chiral, symmetry breaking, at IR. Because once you go to IR, the theory becomes strongly coupled. So no longer perturbative analysis is valid. So you need to include so-called non-perturbative analysis, and then as the experiment and the nature will tell you that the QCD should have these properties at IR. But this is really difficult problem. To solve because of the stronger carbon analysis. Okay, so that's the case. So that's the case. And it's, so for instance, once you start, so beta function, so this, okay, maybe I should write down here. So this is UV fixed point case is no longer. Beta of lambda and lambda. So at UV lambda equals 0 and beta goes to 0 because it becomes free theory. But once you decrease the energy, it becomes the beta function negative. Okay. So beta function negative as you decrease the energy. But if some non-quantum effect or some quantum effect somehow bend sometimes bend this this curve, then here this point is lambda star is called beta lambda star equal to 0 is called is when mu goes to 0, now lambda goes to lambda star. So this is called R fixed point. So as you decrease the energy, the beta function of course increases, but the quantum effect will sometimes bend this curve and it goes to here. That's called our fixed point. And as you decrease the energy, so you reach to this point. Then, so once beta function is 0, coupling constant no longer run. So that's called our fixed point, and this is one of the examples. 5-hole theory and 5-hole theory and the coupling constant lambda in dimension d behaves like this way. When d is less than 4, so first you just when lambda is small enough, this is sublinear, right? Sublinear, so that it decrease by linear order. But as the lambda goes to lambda becomes bigger, then so this second term becomes dominant. So therefore, it becomes so this is negative, this is positive. So therefore, it just curve becomes bent, okay, and it reaches to the point here. And where in 5-hole theory, this lambda star is given by 16 pi squared over 3 4 minus 3. So you just solve beta lambda star is equal to 0. Okay. So this point was first point of Wilson Fisher. So therefore, sometimes, so this point is called R fixed point, or sometimes it's called Wilson Fisher point. Wilson Fisher fixed point. And as you can easily see this, so this number is no longer small when d equals 3 or d equals 2. Therefore, the perturbator analysis is not it's no longer valid, and then so this one you have to include the gamma. That's what I tried to explain. Sorry. Let's see what I tried to explain. Okay. Any questions so far? I'm sorry about this part. I just told you wrong. Yeah. Any question? So, I think I explained the so I explained to you the how the coupling constant depends on the scale and also coupling constant and also beta function, and how the theory behaves depending on the sign of beta function. Of course, as I mentioned, so if beta of lambda equal to 0, then this is called exactly marginal constant, and the theory is conform. So it's called conformal symmetry. So therefore, this point is very, very important. For instance, this even Wilson-Fisher point is also conform. So that, and also if you have a conformal the conform field theory, it has the symmetry is enhanced. It's no longer Poincare symmetry to the conformal symmetry, but it's easier to analyze the theory. Okay. So therefore, the conform field theory indeed appear at a fixed point, and also so therefore the special point of the space of QFT. The space of QFT is parameterized with these coupling constants, but at some particular point, beta function vanish and it becomes theory becomes conform. Okay. Okay, so I think I explained to you about the behavior of the coupling constant and so on. Okay, so far there's no question. And the Wilson-Fisher point is that appear in the Peskin-Schroeder 12 point, the last section of the chapter 12, and then the application to the statistical mechanics is given in the chapter 13. But I'm not going to go into the detail about the chapter 13. But instead, I miss one important topic, which is called the Coleman-Weinberg. Potential. Effective potential. So that's in fact it appears in Peskin-Schroeder chapter 11, but I mean. The treatment of Peskin-Schroeder is a bit more involved, and because they use OM model. So, but I'm going to follow this. This is indeed Weinberg, and I'm going to follow the Steven Weinberg textbook. I think it's 6.2, as far as I remember. Just this is a question mark. Just look at the Weinberg's textbook, volume 2, and then if you look at the contents, there's a section called Coleman-Weinberg potential. As far as I remember, it's just 16.2. I don't, maybe I'm wrong. Just correct me if I'm wrong. So the Coleman-Weinberg effective potential. I'm going to follow the Weinberg's book instead of Peskin-Schroeder. Peskin-Schroeder is ON model, but the Weinberg just used the FIFO theory, so it's much easier. So the difference between Wilsonian effective action versus so-called 1PI effective action, which we call gamma of phi, is as follows. So with some effective action, we just integrate out all the momentum k, which is lambda to mu, right? So we integrate all the momenta. So all the momenta whose region is in between mu and lambda. So the quantum effect is really taken care of only on this region. But whereas for the gamma of phi is gamma of phi includes essentially, in principle, includes all quantum correction. In principle. So the 1p effect reaction and Wilsonian effect are a completely different thing. So Wilsonian effect reaction is just integrate out some energy region, whereas the 1p effective action is just include all the quantum correction. I mean, we already see in 5-4 theory, even quantum electrodynamics. We just consider the effective action, the general function, and take log, you get the effective action, and take Legendre transformation and to get the 1p effective action. And 1p effective action essentially contain all the quantum 1pi, as I explained to the second lecture, all the quantum diagram, which is one particle irreducible diagram. Okay, so in principle, it encodes all the quantum correction, gamma includes. But in practice, it's very difficult to compute gamma. That's a really difficulty to compute 1p action. And then what the Coleman-Weinberg did is just find the one loop order to compute one loop order gamma phi in the 5-4 theory. That's what Coleman-Weinberg did. Yeah, as I mentioned, so it's written in chapter 11. It's an important topic in Person Schroeder, and somehow I omitted it. So I'm going to explain and take a break after that. So we start the Lagrangian of 5-4 theory, which already seen many times. And then, so this is very Lagrangian. And then again, I use the write down. So in terms of the counter term and so on, phi square minus 1/2 and square phi square minus lambda 4 factorial phi 4 plus the counter term, where the counter term is given by 1/2 and z minus 1 or delta z. Oh, sorry, I think maybe I should have done that one. So we would like to compute the effective action gamma phi j, or some people call phi Glasgow or phi Glasgow. Some people call phi Glasgow. In my previous lecture, I call it phi j. So which just take the perturbation around the phi j. So we just rewrite this action, so this action by just write down phi j plus phi, then what you get is, and phi j treated as a constant, n square phi j square minus lambda 4 factorial phi j to the fourth plus phi minus n square phi j minus lambda over 6 phi j cube, and then you have the kinetic term minus 1/2 phi square n square plus lambda over 2 phi j square, okay, minus lambda over 6 phi j phi cube minus lambda 4 factorial phi to the fourth plus counter term phi j. So I just plug this one into here, and it just expand. And I just treat phi j is independent of x. So therefore kinetic term only depends on acts on phi here. Okay, and this Lagrangian, so what I'm interested in the following part. So this part, and this part, and then this part. So this part, and then also this part. So the rest of the part indeed do not contribute to so-called one loop effect. So I'm going to, so the relevant part for one loop diagram is only this yellow part. The rest of the part is irrelevant. That's what I'm going to ignore. So in fact, so therefore, so if once you just integrate out, so for one effect, this yellow part is relevant, and then what I'm going to do is as follows. So the effective potential of so e to the so what I'm going to consider is as follows. E to the I d for x 1/2 partial phi square minus 1/2 mu square, so the n square plus lambda half phi j square and phi square. So that's the part which is depends on phi, and the rest of the part is just constant. So I'm going to, so this one is out of the integral. So this, I just take the path integral over phi, this phi, not phi j. It's because it's constant. So I just first keep this one as it is because it's outside of the path integral. Just let's consider this. Then you can just perform the Gaussian integral. So as we did many times, so this is give you some number times determinant of 1/2. So this is just if you do the so this can be written in terms of phi 1/2 box plus 1/2 n square plus lambda over 2 phi j square and phi and minus sign e to the and this e to the integral. And perform the Gaussian integral, you get the square root of determinant with this one, with this operator is here. Okay. And this can be written in terms of, again, use the same trick as we did many times. In the first lecture, so this becomes 1/2 m squared plus lambda over 2 phi j squared. Okay. So log that can be replaced trace of log. Okay, so that's what I have used. Okay. So we do the Fourier transformation. So we're going to take the Fourier transformation. So I use. So therefore, if you use the Fourier transformation, what we are going to get. So this is will give you so-called effective potential e to the V1. Or what I want, gamma phi e to the gamma of phi j. Essentially with some number. So therefore, gamma of phi j. Maybe I should call. So later I'm going to include this contribution. So therefore, let's take a gamma tilde. Let's call gamma tilde. Gamma tilde of phi j can be written as follows. If you do the integral, so this is d for p log minus p 2 pi to the fourth log p minus p squared plus 1/2 m squared plus lambda over 2 phi j squared. So I just take the compare the exponent and then take the Fourier transformation of this one, and maybe I should include minus 1/2. Yeah, minus 1/2. If you put the minus sign, I don't need to use minus sign. Okay, so that's the you would get. Okay, so that's the what you would get, and I think I should put the I sign here. Okay. So then I'm going to do the wick rotation. So I'm going to do the wick rotation. So then wick rotation. To get the Euclidean signature, and then so what you will get is but I will cancel with wick rotation the zeros component the momentum. Then this will give you d for p Euclidean pi to the fourth log p squared plus this part 1/2 m squared plus lambda 2 phi j squared. And then I don't know why I didn't do that. Let's call this part is mu phi j. So this one equals mu phi j, and so therefore mu squared. So therefore this one is mu squared phi j, and this one is mu squared phi j. Then I just want to perform this integral, but to perform integral, you just do the following thing. So the d q gamma phi j of d mu square of cube. If you do that, then you just take the 3 times of this mu square derivative so that you get the d cube equal 2 pi to the fourth p square plus, of course, pe square mu square phi j and cube divided by 1 over divided by this one. If you apply the three derivative on this one, I just want to perform this one, but to do that, it's better to take derivative, and then one can perform this integral 0 to infinity dpe 8 pi square, which is pe cube divided by pe square plus mu square phi j and cube, which is 1 over 32 pi square 1 over mu square and phi 0, phi 0. Okay, then so therefore, if you take the mu square integral 3 times of this one, what you will get is, let's go, gamma tilde for phi j is equal to 1 over 64 pi square mu to the fourth phi 0 phi j log mu square of phi j plus some constant mu square phi j plus p mu force phi j. So as you can easily see that if you take the mu square derivative 3 times, you get this one. And the a and b are integration constant. So so what I have done is essentially to compute one of the effect to the 1 pi effective action, you just perform the Gaussian integral, and that will give you a trace of log of this operator, and then perform an integral, you get this one. And indeed, this part usually contain divergence. It usually contains divergence. So as you can easily see, so this usual integral log of p square and d4 to the p usually contain divergence, but that cancels with the counter term I have written down. I already erased the blackboard, but the infinity, which is included a and b, are cancelled with counter term, and what's left is what's relevant this term. Okay. And restoring the 5j dependence on last time, I already erased the yellow part, so what you will get 1/2 m square 5j square plus lambda 4 factorial 5j to the fourth plus 64 pi square, and then mu to the fourth this time, fourth and 5j and log mu square on 5j. Okay, so this is the one of the effect to this effective action. So this part is Glasgow one, which I have keep outside the path integral, and then one of the correction really come from Gaussian integral you perform here, and this divergent pair cancels with counter term, and then what's left is this one of effect. So this is the one of contribution to the effective action, 1 pi effective action. That is called Coleman-Weinberg. So this is called Coleman and Eric Weinberg, not Steven. Potential. Yeah. So that's the one concept. Okay, so So let's get started. So this one is, I just checked now that it's a Weinberg section 16.2, so it's okay. If you have a question, just ask me, or you can just consult section 16.2 of Stephen Weinberg. Okay. Okay, let's erase this one. Yeah, by the way, yeah, Coleman has passed away, I don't know when. And also, Coleman has passed away, and also Dyson has passed away. And also Gelman has passed away. All these big figure in quantum field theory has passed away, unfortunately. Anyway, so I told you the name Gelman. So Gelman is Gelman and Coleman are the really, and also Weinberg too, among the big fields who create, who build the quantum field theory. And Gelman made a huge contribution to the QCD. And then QCD, and I'm going to explain. So the QCD is described based on the quantum Yang theory. And to do that, first I need to explain the classical Yang. And also, the electroweak theory is also based on the Yang theory. So let's recall the electrodynamics. So the electrodynamics, EM, electromagnetic theory. In other words, BDM. Okay, let's. So I begin case 3. So as we learn, that for instance, so you have Lagrangian of free Dirac field. So this has the symmetry, the U1 symmetry, which rotates e to the I alpha or some people just write down like this way. Okay. So the psi bar is of course is without minus I e alpha of x, and it's invariant on the U1 so-called global. Global means that the alpha is independent of position x. So now it's independent. And you can make it local by just alpha goes to alpha of x. But you need the cost of that. So usually the people just do the the ordinary derivative partial mu of psi of and tensor with some vector n is just a limit of epsilon goes to 0, 1 over epsilon psi x plus epsilon, so x mu and mu epsilon minus psi of x. Okay. So this is not a good object because so for instance, let's call the psi of x is mapped to e to the minus I e alpha of x. This means because this becomes local U1 symmetry. Local means it depends on position of x. Okay, position space time of psi of x, which we call u of x, or maybe b of x, whichever color. E to the minus I e alpha of x. Oh, sorry, no. Psi of x. And if you compare, so this partial mu psi that appear in Lagrangian is not good object for local symmetry, because here you just psi is mapped to u of x under this local symmetry, whereas here is mapped to u x mu plus n mu epsilon phi of x. Okay, under this local symmetry. So the position, if it depends on position, you cannot compare. Okay, after this local U symmetry. Okay, so to make a bridge between them, so we introduce the following object. So so-called Wilson line. So this is the which we call Cy of x, such that the Cy of x of psi of x is transformed under the following way: u of y, Cy of x, psi of x. Okay. So we introduce so-called Wilson line such that if you multiply this Wilson line to the psi, then under this local U1 symmetry, so this is local U1 symmetry, this is local U1 symmetry. So this is local U1. Oh, by the way, by the way, do you understand what the U1 symmetry means? Do you understand the definition U1? I hope you do. So U1 is some number, complex number C, such that let's go A, such that the norm C. Okay. So this form the group. Okay. So group. I hope you understand the definition of group. In any case, so which means this unit circle, this real imaginary, it's just unit circle. This is U1. So then, if you introduce this object, one can just compare, just insert this one into here by the following way. So let's define, so-called this is covariant derivative, is defined limit epsilon goes to 0, such that the 1 over epsilon psi x plus n e epsilon minus c x plus n epsilon x psi of x. Okay. So just include some Wilson line that bridge the point x and y. Okay, such that the under local U symmetry, it both behave the same way. Both behave the same way. So under the transformation local symmetry, so that this d mu of psi is indeed is transformed. So no problem about. Of course, if epsilon goes to 0 means u of x of d mu of psi. So Wilson loop indeed. So therefore, it transformed under local symmetry of u of y, and then c of y x, and u inverse of x. Okay, so that's the. For instance, if you take the infinitesimal, so if you take the Taylor's c of x, y of x, or this one, x plus an epsilon x can be written in terms of 1 minus r e and mu and times epsilon. Okay, plus order e squared. So just take a Taylor expansion. Taylor expansion in epsilon. So it also depends on n and epsilon. If epsilon is small enough, you can just do the Taylor expansion, and since it's n is a vector, somehow has to be contracted with some other vector. And of course, there is some u1 encode the constant e. So I just incorporate e here. So once you plug this one into here, so then this can be written in the following way. So if once this one plug into here, what you will get is that this one is equal to partial mu psi plus I epsilon and mu psi of x contract with n mu. So that's what. Oh my god, sorry. This is e. Yeah. Okay, so that's the, as you can easily see, so one if you plug down into here, take the derivative, epsilon goes to 0 will get derivative, but there's a one linear order epsilon in second term that will give you just second term. Okay, so that's the covariant derivative what we found, what we saw in the QED covariant derivative. So that's what we saw in the in the presence gauge field. So therefore, so in the QED, so this one is for d slash of n of psi, and also you have to include so-called the gauge field Lagrangian f mu. That's a Lagrangian for QED. Lagrangian QED. That is the. So therefore this one is invariant under the local symmetry. But to see that, I just want to go beyond that. Indeed, so it's a very for some people it may be too easy, but let me move on. So by using this relation, one can just write down the following way. So this one, when y is equal to x plus n epsilon, so this can be written as follows. So so this C of x1, so under this transformation can be written as follows. So U of x plus n e epsilon C x plus n epsilon x U inverse of x. Okay, and plug, take a tail expansion and plug that into here, and what you will get is a U of x plus epsilon and mu, partial mu U, and 1 minus I e a mu and mu times U of x and U inverse. Okay, and this will give you that the U x and mu in leading order. U inverse and then sorry, I just compare. I'm very sorry. So there's an epsilon here. Okay, and then so you just compare all the epsilon part. So that the what you will get is that the where can I erase? So mu, you just compare all the epsilon part. So all the epsilon part and all the epsilon part of this equation. Then so what you can first find is that Ux and mu U inverse is transformed Ux and mu U inverse. Okay, and also I have this is dependent on epsilon, and then so it's 1 and U inverse. So what you have to find is the plus I e partial mu U and U inverse. Okay. So this is the transformation under this local U1. And since this is the U is U1 group U1, mu is just vector. So it's just a this is just number with unit norm, and the mu is just vector, which is the some 4 vectors, so that they commute. Okay, they just commute. So therefore, so if you look at the mu is some one element, 0, 1, 2, 3. So one of the element is just not number. So they commute. So therefore, commute means abelian. Yeah, they commute. So therefore, U can be bring to here, and U inverse cancel, so that the mu is mapped to mu plus I e over E, and you just plug the definition here. Okay. So this U is equal to e to the minus I e alpha x, but what you will get is partial alpha of x, and the minus IE cancels IE, and you get this one. Okay. So this is the gauge transformation. Transformation of the electromagnetic or gauge potential. People call it. Okay, but so later, so that now later, so we will how to say elevate this mu to the matrix value, and U becomes no longer just complex number. It becomes matrix value. If the matrix value AB is no longer B. If AB are metrics, it becomes non-commutative. So non-abelian. So that these parts no longer give you the A mu. So you just have a U inverse. And later, so this part does not simplify like this so easy. That's what we're going to do. So this is very important form you need to remember. And furthermore, so let me erase here. So just rewrite everything of electromagnetic magnetic theory in terms of abelian, in the language of abelian gauge theory. So then, so as we learn, so the d mu of psi of x is under this local U1 or gauge. So this local U1 symmetry is indeed a gauge transformation. A gauge transformation U of x d mu psi of x. So what if you apply other two times, okay, d mu and d nu, which is d mu minus d mu acts on psi of x. Okay, so then this is transformed the following way. So U of x so I just insert, so since the d mu of psi is just transformed, you just apply U, right? So even if you apply twice of this covariant derivative, the property is the same. So instead of writing 1 here, so it's just the counter. So 1, so I just insert U inverse U in here. So then, so therefore, under gauge transformation, so this d mu or local U1 transformation is transformed d mu U inverse. Okay. So that's how it transformed, and it's a direct calculation to compute this one is Persian mu plus IE and mu, and Persian mu IE and mu, okay. And then this is, as you already know, that this is I times E Persian mu and mu minus Persian mu and mu plus I epsilon and mu, which so I on purpose introduced this commutation relation, but in fact, for just if this is just a only 4 vector, or just if you fix mu and mu, it's just number. So a mu minus a mu. So this is the commutation, right? It's 0 indeed, 0 for just U1 gauge theory. But therefore, this is Persian mu and mu minus Persian mu and mu and times IE. Okay, so that's the field strengths of the gauge field. So this we call it IEF min. Okay, so therefore F min nu. So from here, so what we have learned is that the F mu nu is transformed U F mu nu U inverse. Okay? U inverse. But again, so this is U1 and this is just number once you fix mu and nu and U inverse, this will give you just a F mu nu. Okay. Therefore, so you can just bring U inverse into left to left or bring U to right and they cancel each other. So it's just F mu nu. Therefore, unlike the local U1 or gauge transformation, this part is invariant under the gauge transformation. However, so from now, so we will think this A, so this A takes a matrix value. So for instance, so A mu takes the following form: A mu 1, A mu 2, A mu 1, A mu 2. So A mu just stands for this matrix value. Okay. Then and U is also some group, some matrix. For instance, 2 by 2 matrix. Then they no longer commute. They cannot swap. That is called non-abelian or non-commutable. So therefore you cannot swap. So this part does not go to this just mu. The same as here. Here. Now, if you actually, okay, let's move on step by step. Let's move on to here. So mu is if the matrix value. So mu and nu is no longer equal to mu. They're no longer 0. So you have to keep this term. So therefore F mu nu also takes a matrix value. Okay. So that the so this, if you look at the gauge transformation for field strengths, so this is matrix value, even though if you fix mu and nu. Okay. Here now, I mean, so usually when you say A mu, you just write down A0, A1, A2, A3. This is a 4 vector you may assume. But this one is already fits into here. You fix mu, okay? So that if you vary 0 to 1, so it becomes 4 vector, 4 vector, 4 vector, 4 vector. Like this way. But now I fix mu here. Okay? So there's the same thing. So that if you fix mu and nu, still F takes a matrix value. So it doesn't mean that the F is something like a 0, 0, 0, 0, E, 2, 3, minus E1, and so on. I don't mean this matrix value. F, once you fix mu nu, for instance, this E or something, or B or whatever, once you fix mu nu, it still takes a matrix value. So that, and also U takes a matrix value, so therefore they no longer commute. Okay? So therefore, so gauge transformation does not reduce this to F mu nu. So therefore, if you F mu nu is matrix value, this is no longer gauge invariant because it still have sandwich by U and U inverse. Okay, so you have to be a bit clever. That's the beginning of the Yang-Mel theory. And so to explain what the matrix value means, I need to explain Lie algebra and Lie group. So that's how I'm going to explain. So this Lie algebra, so this and Lie group means somehow it's group that is formed by some matrix which satisfies some particular properties. Any questions so far? So I just rewrite everything in terms of abelian, so in the sense of abelian gauge theory, or you rewrite electromagnetic theory in terms of abelian gauge theory. Oh, and I need to introduce the notation. So mu is in physics it's called gauge field, or gauge, and sometimes it's called vector potential. But here people call it connection in geometry, and this F mu I call it here is called curvature. I think this semester Yue teaches differential geometry course, and then you will learn about the connection, curvature, and so on. And so the theory of vector bundle and so on. And I think I oh my goodness, did I erase? Unfortunately, I erased. I think I should explain a bit about the Wilson loop a little bit more. So Wilson loop I introduced is I already here it's a Wilson loop. Oh my goodness. So Wilson loop I introduced should satisfy the following properties. So so if you assume y of x is y c x y and dagger. So if you take the complex, in this case just complex conjugate, so you just go from connect psi of x to c y x psi of x, then this will behave like a y, cy of x under gauge transformation. And here, whereas even though this one is, that's how we introduce the so-called Wilson loop. And in infinitesimal order, so this Wilson loop is just the by Taylor expansion of epsilon. You can write that like this way. But in general, so the u of this, so c of yx can be written, c of yx can be written as follows. Okay, maybe if you assume this fact, so you can just write down the following way: minus I e x I e n mu epsilon plus order epsilon squared. So that's what you can just assume. In general, so you can just write down. So if you have the space time and the position of x and y, okay. So and the path from. So now what we are doing is just the epsilon order path, epsilon. You just connect like this way. Epsilon. So that you just integrate over, so this leading order. So in general, c of yx is just the path from x to y ds dx mu ds. Oh, I'm sorry. Is of course exponential. So you just sum over all epsilon by depending on path how you connect from x to y, and you have to include minus I e epsilon okay, minus I e. So this is the usual form of Wilson loop, and to integrate out, you can usually ignore the epsilon square part. So this is called Wilson loop. So here x to y depends on really path c. Okay, so that was I shouldn't use C, sorry. Let's go gamma. Gamma is pass. Gamma from X to Y. Let's go Wilson loop. And then, so this field strength indeed is the somehow will tell you that how to take the path. The difference, so I just want to keep this one. Let me erase this part. Suppose, so this is space-time, so that I've written down over there. So if you have space-time and you start with X, okay, and you just go to first vector epsilon 1, vector epsilon 1, and go to epsilon 2. I mean, it's very similar to what you have done in the general relativity to compute tidal force. People already know this. Or you can just first take epsilon 2 in vector and epsilon 1. You can have two paths. Path 1 is take first E1 and E2, or other path is E2, E1. So you can see the difference between them. Or in other words, so if you take the difference, you just go into one and come back. You can just, I mean, this minus this is just a circle, right? This path minus this path is just a circle. So then one can just do the same thing. So if you try to measure exponential of this, so gauge C, so let's call this one x1, x2, x3, x4. So I want to compute the Wilson line x2, x3, x4. Not x4, x1. So as I mentioned, so this really depends on gamma. So the path you take. Okay. So take x1, x2, x3, x4, and x1. Sorry. Okay, then so this is just plug. Each path will give you exponential I to the, and you have to be careful with this which epsilon you take. Essentially what you would write down is equal to exponential minus I E, and then I mean, you can just project to for instance, you can project to the 1 and 2 plane, so that the one can write down the following way. So first you go to A1 direction, x. I hope I'm not mistaken. And next goes to epsilon 2, right? X plus, so epsilon 1, and then next is just go to E2 direction, so that the A2 x plus epsilon 1 plus epsilon 2. Then you have to do the next is minus, so minus A1 x plus epsilon 2 and minus A2 of x, So you just come back to the original point is x. And you have to include appropriately the epsilon here. So assume that the length is epsilon. Okay, so this is the case, and take the tail expansion, and take the tail expansion, the epsilon 1 and the epsilon 2 goes to 0, then this will give you something like a minus IE epsilon square and partial 1 and 2 partial 2 A1 plus all the epsilon square. Okay. So that's what you get. So the difference between yellow and blue line for Wilson loop is measured by the curvature given here. So this is essentially what you do the same, essentially the same thing as you compute the tidal force when you learn GR. So essentially this mu corresponds to Christoffel symbol, and then F mu nu is called curvature, corresponds to the Riemann-Rich curvature. Yeah. So that's the, in fact, this in Riemannian geometry, gamma mu, and it depends on other variable nu rho, right? This nu rho is matrix value, which means mu nu, and also you have another two indices, so maybe rho sigma will give you another two indices for Riemannian curvature. So this gamma and R is connected to so-called tangent bundle. Where is this tangent bundle and the metric on it? Whereas the gauge field A and the field string F is some other so-called vector bundle, principal G bundle. Or in this case, the abelian gauge theory, it's called line bundle or U1 bundle. So that's the theory of so-called vector bundle, which was constructed around the mid-1930s, and it took like about 10 years in mathematics to completely formulate the language of the language of vector bundle. And then yeah, so people like Whitney, like Seifert, and some big mathematician in early 20th century constructed. And there's a book by so-called Steenrod about the theory of vector bundle. And Jan Mills and Mills just learn the language of vector bundle and try to construct a similar theory of this Einstein general relativity. So Jan Mills tried to construct the similar theory by using the theory of vector bundle. That's how the Jan Mills theory starts. Okay. As I mentioned, so this Wilson loop, the difference between the path is measured by this curvature. So that's the what appeared in the expansion by epsilon order. But as you can easily imagine, that from this construction, oh gosh, I don't have time to talk about the Lie group and Lie algebra. So if you use, so as you know, so d mu acts on a mu minus d mu is it correct? Yeah. So we'll give you f mu, right? Yeah, I think that went wrong. And the Wilson loop exponential of the minus IE, the path ds, dx mean and ds a mean. So this can be written in terms of if gamma is just a loop. If gamma is loop, for instance, gamma is loop, so this can be written in terms of the gamma is loop, and the sigma is inside loop. It's just by E Stokes theorem d whatever sigma mu at mu. But this is Stokes theorem. So that's what essentially did in this step. I just do the Taylor expansion just to look at on the leading order. But in essence, what we have done is just Stokes theorem in here. Okay, so let me just briefly introduce the Lie algebra and Lie group and stop. So what we are going to do is as follows. So here I did just describe the theory of the U1 gauge theory to arbitrary G gauge theory, where the G is the Lie group, or the connection will take the so-called Lie algebra value, or gauge field take Lie algebra value. And to do that, I need to explain what Lie group is. I'm going to erase here. So any questions so far? Nothing. No question? Okay. So I think you will learn the detail about the differential Lie group and Lie algebra in the course of UUE. And also, if you don't, anyway, I taught the differential geometry course 1 year ago. Maybe next year I'm going to teach, I don't know. I'm not going to go into too much mathematics. I just give you some basic explanation of the introduction to physicists about the Lie group and Lie algebra. So to this end, so in this course, I'm not gonna explain the complete the precise definition, but what I'm going to explain is as follows. So I'm going to only talk about the application to the quantum field theory. So that now matrix Lie group. I'm going to talk about matrix Lie group, which is a subgroup of this is not precise definition. So please bear in mind R or G, L, and C. A pro subgroup of. So this is general linear group. So the GL, so definition of GL and R is just a matrix and So this is n by n matrix with the real coefficient, and the determinant of A is not 0. So you have inverse, and that it means. And for instance, one can just take the SON is the matrix of GR and R such that can I erase? Sorry, A transpose is 1 is A transpose. And if you want to go to C, you just replace R by C. So this is SON. Oh my goodness, I think I told you wrong. This is just ON. 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 And SON is A, G, ON such that determinant A is equal to 1. So from here, of course, determinant A is what? Can you get understand that? This is either plus minus 1. If you pick only plus component, you get this one. And the unitary group is A, which is GL and C, such that the A, this is transpose, but take dagger. No, take complex equation and transpose. So because it's the base field is C. And as you can easily see, what's the determinant of A in this case? Is what? I hope you understand. This is U1 inside U1. So then if you pick only the one part special unitary, it's called A, G, L, and C. It's not inside. U and C. If you pick only one part in the determinant, you get a special unitary group. So this is orthogonal, special orthogonal, unitary, special unitary. There is a so-called symplectic group, which I'm not gonna, which doesn't show up in the in these lectures. I'm going to omit. But these are, and also special linear and R or and C is just that A, G, L, and R and C such that the determinant is 1. So this is special linear, a general linear, orthogonal, special orthogonal unitary, special unitary, symplectic. I'll give it to you exercise. You can see the definition. Symplectic group. Okay, so that's the essentially Lie group which show up in this in this lecture. And for instance, SO 1,3. So this is a Lorentz group. So I didn't explain. Okay, Minkowski signature. So OS. So this is Lorentz group. So this is in the A is MN and sorry M4R or M4R such that the A 1 minus 1 minus 1 minus 1 A transpose is 1 minus 1 minus 1 minus 1 which is equal to A 1 minus 1 minus 1 minus 1 So this is Lorentz group. Essentially, if you put everything plus, if you put everything plus, it reduces to SO, right? Here, SO. Oh my goodness, I think I should also put the determinant of A is equal. So essentially, if you put all the plus, use the plus sign, it reduces to SO, special orthogonal. But it depends on the how you choose the sign. You got the Lorentz group. And in particular, it's not the topic now, but SO 1,3 is indeed the same as SL 2C. Am I correct? Yeah, I think it's correct. Yeah, I think it's correct. Isomorphic. I'm not going to explain what's anyway. Yeah. And so on. So it's not the course of group theory. So I'm not gonna go fully in detail. But those are the characters that appear in this course. Okay, and then so almost time. Let me introduce Lie algebra. So Lie algebra, indeed. So these can be understood as so-called the manifold. So I hope most of you already know the definition of manifold. I mean, general linear group is essentially the R to the sum n square. So, and then take the n square element and take determinant of the coordination round locus. Am I correct? Just a moment. Yeah. So, yeah. So essentially, as a manifold, its general linear group is R to the n square minus R to the n square minus 1. So it's open manifold, and it's a subgroup. It's cross subgroup. It has a form of manifold, and the Lie algebra can be understood as a tangent space of this manifold. But that's too formal. So the way you can understand it follows. So the algebra is a following way. So given a group G, so this Lie group or this matrix Lie group, one can generate so-called Lie algebra G such that the Lie algebra. So this is so German G, German small g, the algebra such that the G is some x, which is let's see, and R, such that, for instance, e to the for energy. So you can understand in following this way, where of course e to the x. So this is the matrix value. So e to the I x is just a sum of x to the n factorial, n is equal to 0 to infinity. So it's just a matrix multiplication. So for instance, literally GLN, so GL and R. So from GL and R. So the algebra of GL and R is indeed in fact any matrix, n by n matrix. So for instance, if you put any matrix on here, determinant no longer 0. Okay? So it's because it starts with 1 plus something, right? So it starts with 1, and so therefore it can be any matrix. If you put an exponent, the determinant no longer 0. So therefore, if this is the case, and the question is, what are those Lie algebra? And I'm going to write down. So therefore, I'm going to get rid of it. Oh, I'm sorry, I've already erased the definition. Okay, so you can just take a look at the recorded video later. So ON, so the ON, so this is Lie algebra, ON, can be understood as the A, which is matrix value of R, such that it in fact, both are the same, so SON, sorry. I mean, it has two components, so, okay, so, I mean, the algebra of ON does not make so much sense. So, let's consider SON, okay. And so, also here, so, UN, German UN. It's hard to write the German letter. UN is given by X and C such that XT is equal to minus, oh sorry, dagger is equal to X. And also here, SUN is the same of UN, but you just, you have to impose determinant A, and determinant A is, of course, as I mentioned, e to the ITX determinant is essentially e to the trace of X, right? IT. So that the determinant is equal to 1 means that the trace has to be 0. So trace of X is equal to 0. And of course, this automatically, so the SO automatically mentions trace of X, A, is 0. So therefore, the automatic determinant condition is satisfied. For instance, here is L and R or C is given by some matrix A, which is M, N, R, or C, such that the trace of A is 0. Okay, so let's see from Lie group Lie algebra. That can be understood tangent space and so on. And so the important notion about in the Lie algebra is one can define the commutator. So G has so algebra means you have the multiplication. In this case, multiplication is given by the hash in the commutation relation. So this X and Y is given by, is mapped to X and Y, which is just a ordinary commutation relation. And as you can see that the even though you take the commutator of X and Y, any element of X and Y is still the element of G. Okay. So for instance, if you look at the SL definition of Lie algebra SL, its trace of A is 0, right? But if you look at the trace AB minus BA is trace of A AB minus trace of BA. And of course, you can swap them. This is 0, right? So therefore, even if you take the commutator, you get 0. So that it's satisfied that it's in the element of SL2. It's the same thing. So that you can just check that the SO, if X and Y satisfy the SO condition, where was the SO condition, and take the trace xy minus yx, and take trace, then you get the x trace, y trace, minus y trace transpose, transpose, x transpose minus x transpose, y transpose. And so we can just use this property that the transpose of x is just a minus x. So therefore this is yx minus xy. Minus cancel. But it's an element inside the SO. So this commutator preserves the property of Lie algebra. Okay? This is the property of Lie algebra. So the commutator does not destroy the property of Lie algebra. So it's important. So the product structure in the, for instance, if you have a number, just number multiplication is given by c times c goes to c. Number x and y is given by just multiplication x times y. Okay? It's the same thing. So the multiplication is given by commutator. G, 2 copy of G will give you another copy of G, another element of G. This multiplication is given by. So that's form algebra, so Lie algebra. And addition is just ordinary addition, or as a matrix. So that's the notion of Lie algebra. And then, so I'm out of time. So here, as you can easily check that if you have a 3-element x, y, z inside a Lie algebra G, you can have the Jacobi identity, and everything is equal. And then here is the x, y. This is equal to 0. This is called Jacobi identity. That's the original. Okay, so that's the basic of the group and the algebra. Okay, let's stop here. If you have a question, just tell me. Do you have a question? I'm waiting for your question. If not, I will stop. Whatever. Oh, by the way, I have already posted homework 3. And then you're supposed to submit the homework 2 before the lecture. Homework 3 is about YAMLs on the algebra group. Just send me a message if you have a question. I don't know how many people were already watching. I really wish this live stream really works. How was the network today? Was it okay? Seems like there is no question. So I will stop in that case, and then you can ask question via WeChat later. Okay, thanks for watching. If you have, okay, bye bye. Oh, there's a question? For me, it was okay. Okay, bye bye.